So do you hear me now? Or?
Yes, there's a bit of an echo, but yes.
And now?
Yes.
Okay, so our next speaker is David Dowe, who will be talking about the Titan, but yeah, you can go ahead.
Thank you, Boumediene. There's a slight echo, and for what it's worth, sometimes I wasn't able to hear the questions that Jean-Louis was being asked. But look, firstly, thank you to the organisers and Boumediene in particular, and I hope I'm not mispronouncing your name, or that if I am, I'm not doing it too badly. Thank you very much for the opportunity to speak. I'm not in the best of health at the moment, so I don't know how many times I might cough. We will see. And my slides could be better prepared, but I hope they will be adequate. So I'm at Monash University. I hope you can see my email address here in Melbourne, Australia, if any of you wish to contact me to comment and conceivably collaborate. So I'm joining you from Melbourne, Australia, on the lands of the people of the Kulin Nations. And I take advantage of this opportunity to acknowledge them as the traditional owners and their ongoing connection to the lands and waters and their elders past and present. We are today, of course, also joining from other countries across the globe. So algorithmic information theory is often called Kolmogorov complexity, even though Ray Solomonoff surely independently came up with it earlier. So some things I'll talk about in the available time will be minimum message length, what I'm going to call Solomonoff-Kolmogorov complexity, but what we can, of course, call algorithmic information theory, intelligence, some connections that I perceive with deep learning, and some other applications. So I have some questions for you, which I will endeavour to address. And in part, I will be commenting on some of the things from Jean-Louis Dessay's excellent talk. So one is when there's clear historical precedents in an area, should credit be given to the person who was the person or people who were clearly earlier? That's one question. Another question is, let's suppose you have a universal Turing machine and you feed it 50-50 random, that's probability 50% that it's a 0, probability 50% that it's a 1. You feed it random bit string, infinitely long random bit string. Is it guaranteed to stop? Is it guaranteed to go into an infinite loop? Can you say anything about, will it retain its universality forever? Or is it guaranteed with probability 1 to ultimately lose its universality? That's another question I ask you. And the last question I can think of asking you is, if you think of binary sequences, what's the most complicated binary sequence you can think of? Okay, so Ray Solomonoff wrote a technical report in 1960, and my recollection is that he told me that when he submitted his paper in 1964, that the editor said, it's a bit too long, can you split it in two? So he came up with algorithmic information theory in the early 1960s, and he very much had prediction in mind. Now, he called it induction, and people call it Solomonoff induction. I guess it depends what you mean by induction. It's certainly prediction, but it's no secret that Ray Solomonoff was interested in a multitude of theories and combining them all together. So whether or not that constitutes induction, well, anyway, Solomonoff prediction, and of course, people will probably keep calling it Solomonoff induction. Kolmogorov in 1965, I don't believe had any statistical or machine learning ideas in mind. Greg Chaitin wrote 2 papers in 1966 and 1969, and I believe he was actually an undergrad in 1966. On the issue of historical precedents, between the years, so as far as I'm aware, Jorma Rissanen, does anyone know what year Jorma Rissanen first published a paper on minimum description length? I've heard 2 different years put forward. So has anyone got anything earlier than 1978? Okay, we'll go with 1978. I want to show you the body of work that Chris Wallace and his then PhD student David Bolton did in this area before, well, in the years 1968 to 1975. So in 68, the seminal Wallace and Bolton paper, An Information Measure for Classification, includes the words, we suggest that the best classification is that which results in the briefest recording of all the attribute information. Pretty clear what he's saying, or what they're saying, and similar comments are made throughout various other papers, including Bolton and Wallace 1969-1970, David Bolton's 1970 master's thesis, Bolton and Wallace 1973A, 1973B, 1975, Wallace and Bolton 1975, and then David Bolton's 1975 PhD thesis. All of these predated Jorma Riesinen's work. Now, people might say, well, technically, I prefer one party's work to the other or vice versa. And that's fine. I'm just talking about the clear, unmistakable historical precedents. So people will talk about description length, and I can't stop you from calling it description length. But in case any of you aren't aware, there is an absolute clear historical precedence of Chris Wallace and David Bolton by, again, 1968 to 1975. They did all that work, including, again, a master's thesis from David Bolton and a PhD thesis from David Bolton. Pretty clear. Okay. So there are the references to those works in case you're wondering. So after Wallace and Bolton started in 1968, I'm not sure when Akaike first published AIC, but it was certainly no earlier than 1969. I think it was the early 1970s. Riesinen with minimum description length and Gideon Schwartz with BIC don't come along until 1978. So a little bit of history for those who might not know or those who might need some reminding. Now, Solomonoff-Kolmogorov and Wallace certainly made contributions in other areas. So one of Ray Solomonoff's other contributions was his warning in 1967 about the technological singularity that one day we're going to have some computers that are pretty smart, and what on earth are we going to do about it? Kolmogorov, of course, axioms of probability in the Kolmogorov-Smirnov test, and Wallace, cosmic ray data analysis in the 1950s. In fact, if you read Solomonoff and Wallace, it's quite clear that in the 1950s, these people had already showed that they were Bayesians. And that was a slightly maverick position in the 1950s. And yet it's relevant here because the choice of universal Turing machine, I contend, is a Bayesian choice. And Wallace and Solomonoff were clearly from their writings Bayesians in the 1950s. Most of you have probably used a Wallace multiplier in recent times without realizing it. Wallace also worked on random number generation, refrigeration operating systems. And can you answer my question? If you take a universal Turing machine and feed it randomly noughts and ones, each independently and identically distributed, and we go on forever with this, has anyone got any idea of what will happen? Is it guaranteed to stop? Is it guaranteed to go into an infinite loop? Is it guaranteed to lose its universality? And anyone care to make a comment? That's fine. That's fine. Well, if you want to know, you can ask me in question time. So why am I speaking here? Well, possibly partly because Chris Wallace in his 1975 book says very nice things about me. He says, all these people have helped, but I especially thank David Dowe who did blah, blah, blah. So I like that. It's one of my favorite parts of Chris's book. Data is continuous and discrete. Now, we can argue about whether or not there are other types of infinities and therefore could data be something other than continuous and discrete. As far as I'm aware, data is continuous and discrete. So discrete data is something we can relate to quite easily in terms of a Turing machine. But what do we do with continuous data if we're going to come up with a message length or a code length or a description length? So basically, to gloss over this, we can say, look, we're not going to state our parameter estimate to 7,000 million, billion, trillion decimal places unless we've really got enough data to warrant doing that. So the idea is if we've got data set of, I don't know, we'll say 10 attributes and 1,000 observations, for want of something else, we'll say, look, I'm going to state the parameter estimate to a certain round-off error. I can't justify going into infinitely many decimal places. I don't have infinitely much data. How will I choose it? Well, maximum likelihood would say maximize the likelihood function. And indeed, if you look at the 1978 version of MDL and Schwarz's BIC, they also advocate maximising the likelihood function, at least in 1978. What's proposed in minimum message length is that, well, no, you want to send a two-part message, and you can't afford to go maximising the likelihood to 7,000 million, billion, trillion decimal places. If you have some round-off tolerance in your statement of the parameter estimates, the first part of the message, provided you don't state it too coarsely, it won't do much damage to the length of the second part of the message, which is your standard statistical log likelihood. So what's done in the Wallace and Bolton 1968 paper, and they refine it in later works, is working out how precisely to state the parameter estimates. And I haven't included the details of the calculations here, but this paper in the Journal of the Royal Statistical Society B and in Chris Wallace's book, they show a relatively easy calculation that the Fisher information, which in one dimension is the expected second derivative, and in multiple dimensions is the determinant of the matrix of the expected second order partial derivatives. This gives you a measure of how tightly your likelihood function is curving. So if you think about a parabola, y equals 1,000,000 x squared, that's really tight, and y equals 1,000,000th x squared, that's really shallow. Now, if the Fisher information is very large, it means that we've got a curve that's very, very tight, and we can state our parameter estimate quite precisely. If the Fisher information is very small, it means that the curve is quite shallow and that we can afford to not state the parameter estimate so precisely. So that's informally what's going on qualitatively behind the mathematics. So that's broadly, informally, how we deal with continuous valued attributes. Now, the discrete valued attributes, this is a paper of Chris Wallace's and mine in the Computer Journal on a special issue on Kolmogorov complexity. Chris Wallace and I contributed 3 articles, Jorma Riisanen contributed 3 articles, Ray Solomonoff, Leonard Levin, and various others contributed pieces. We say, look, in the most general model, you've got a universal Turing machine. And it was similar to what Jean-Louis was saying. You know, you've got an encoding of your hypothesis and an encoding of the data given the hypothesis. And then one of you asked a question about that. So that's your most general model, your universal Turing machine, but you need it to be a probabilistic Turing machine, because when you're encoding the data given the model, it might well be that the model is probabilistic. So you've got log likelihoods when you're encoding the data. Now, the generality of the universal Turing machine is, well, very general. So one piece of work I did with a former PhD student, we published a paper in 2003, and then a refined version of that paper in April 2005 in a book with MIT Press on minimum description length, actually, edited by Peter Grunwald and others. You can have not just Bayesian nets, but in the leaves of your Bayesian nets, you can have decision trees, and of course you could have more general models. So that's my connection. A lot of my connection to algorithmic information theory. That we've got this work talking about discrete attributes, and that our most general model will be the universal Turing machine, although in practice, we're probably not going to use it very often. and that we can also do continuous valued attributes. So I don't know whether or not you know Searle's Chinese room, but John Searle, I believe he's a Rhodes Scholar, but he had this argument that machines couldn't be intelligent, and I hope I'm representing him fairly. And he said, look, we could have Chinese. Now, of course, there's more than one Chinese language. And we could have a person who's got a lookup table. So a sentence comes under the door, written in appropriate script, and they look at this, and they look up a response in their lookup table, and they send the response back again. And you could have, according to Searle, a long conversation doing this without any understanding of Chinese. And you might say, oh, yeah, but it's the room. And Searle says, look, even if the person memorizes this lookup table, they still don't understand Chinese. Now, this kind of motivated me to get into what is the relevance of information theory, which I'd been working with Chris Wallace on for some time then, and Searle's argument. And Jean-Louis mentioned Greg Chaitin saying that comprehension is compression, and comment about understanding. So when I wrote on this topic, for what it's worth, back in 1977 and 1978, I had 4 sections. I had a section in each of these 4 papers saying inductive learning is compression, and one problem with Searle's Chinese room is that when we speak a language, even if we don't know what a noun is, and even if we don't know what a verb is, we intuitively have these concepts, even if we can't name them. And one reason we manage to get by in our languages, in our first languages, and the other languages we speak, which aren't our first languages, is because we have some notion of a grammar. So we're able to get by because we have a compressed representation. Otherwise, this Searle lookup table is going to ultimately need more words than there are elementary particles in the universe. And if it's using the speed of light to get out to the outer parts of the lookup table, it's going to be extremely slow. So that was kind of my response. And while I was at it, I thought, look, as well as the Turing test, you could get a machine to administer the Turing test. And I would contend that a machine judging the Turing test and a machine administering the Turing test, I would contend that they're the same thing. I'll let others decide. Now, Jean-Louis mentioned analogy and possibly other things in intelligence tests. So I just throw away here this work where we had this simple Perl program of less than 1,000 lines, which could pass intelligence tests. But many questions like analogy, it just skipped. So we gave it a score of, say, if there were 4 options, we gave it a score of 1/4. And it could pass. And I told Ray Solomonoff about this, and Ray's response by email was one of, well, yeah, so what? I'm loosely paraphrasing him. I want to know how it did it. And it didn't do it using algorithmic information theory. It did it by just observing your typical intelligence test question. And I think intelligence tests have moved on quite a bit since then. Now, this one here, and I've got, I was saying to Boumediene beforehand, I've got separate tabs open of various papers and slides of presentations. This paper here kind of makes an argument to do with your difference between one single theory, if you like, your Wallace minimum message length inference, and your Solomonoff grab bag of every theory you can lay your hand on appropriately weighted. And the contention we make in that paper is, look, we humans, we like to communicate with one another, and we like to have simple theories to pass around. So yes, if I wanted to do an optimal prediction, I can't think of a better way, if I have enough time, than what Ray Solomonoff would have advocated. But if I'm trying to communicate with my colleagues, it might be nice if I can say something like E equals MC squared, or for that matter, Newtonian F equals ma and all the Newtonian theories if I need to communicate more concisely. Now, one little thing that I might share with you, and again, if you want some details of things, I will endeavour to pass on, is the notion of Darwin-Wallace distribution. This is not Chris Wallace, this is Alfred Russel Wallace, a contemporary of Charles Darwin, where you have a universal distribution over tasks or environments and a universal distribution over agents. And then you can put them together and have iteration and get a nice distribution there. Now, actually, I'm not sure you can see that. Can you see? You probably can't see that. So anyway, this is the notion of Darwin-Wallace distribution from Jose Hernando Thorayo. Okay, I'll go back to
we see the PDF.
You could see that? I'll go back to my Word document. So log loss got to mention. It's not just a proper scoring rule, but I have argued, I'll let other people decide, however convincingly, that within an additive and a multiplicative constant, in other words, if I take a log loss scoring rule and I double it and add 3, that it's still a log loss scoring rule, that it's unique. So there are a lot of proper scoring rules, but I contend that log loss is unique. And we actually have had a competition based on log loss going back to 1995. Jean-Louis mentioned clustering, and yes, clustering and mixture modelling have certainly been done by minimum message length. The seminal Wallace and Bolton 1968 paper was on clustering, and here are 2 works of Chris Wallace's and mine on using minimum message length for clustering. Now, Boumediene, how much longer have I got?
5 minutes.
Okay, all right. I possibly could stop short to take questions. Let me just outline some papers and then lead you into question time. This paper here says, if you knew nothing about database normalization and someone gave you a table which had attribute 1, attribute 2, attribute 3, so the attributes don't have nice friendly names like student ID and subject ID. If you've got big enough tables, minimum message length will tell you how to do the database normalization. It's kind of nice. For me, it's my least cited paper that I'm most fond of, if that makes any sense. Cairns et al. Wrote a paper, I think, in the Machine Learning Journal, saying loosely, MDL doesn't work. And what we did was we came along and said, well, you can refine MDL, and we had some refined MDLs, and ultimately we put MML in as well. And look, we can't speak for Jorma Rissanen, but we did what we thought he would have done. And the refined MDL worked better than what Cairns et al. Was doing, and MML worked best. We've done some work on time series. And this one I particularly want to mention. It's a relatively recent paper. And what we do is we do minimum message length AIC and BIC first, and then do the deep learning stuff afterwards. We found out that that worked better, and that, yes, MML1 when you didn't include the deep learning, and MML1 again when you did include the deep learning. There's mention of decision trees and explainability. And look, this paper here on doing deep learning on the MML residuals, I think is handy for explainability. We've got these really, really complicated deep learning models. We can get some explainability from the MML, from the minimum message length, and then come back later and do deep learning, like I say, on the residuals. These are decision tree papers. The results are good. And yes, your most complicated sequence, I remember talking to Marcus Hutter about this some years ago. It's basically an infinitely iterated matching pennies. And you end up running into the halting problem. And here are some further references in case any of you want to follow this up. I'm interested in developing collaborations, and I really appreciate the opportunity to speak. And if anyone has any question or comment or whatever, or wishes to see a slide backing up something I'd said, I'd very much welcome that. Thank you all very much.
Thank you.
And I've got about 15 open tabs anticipating slides that I could possibly show.
Yeah, I think we are running out of time. So, and any questions or comments? Or?
Hello, hi. I just would you mind just briefly go over your recent paper in entropy with 2021? Well, what was the you said you were using MDL before the neural networks or something?
Using minimum message length and which predates MDL by 10 years, and AIC and BIC, and indeed BIC is, well, the 1978 MDL, so we were using MDL. Yes, so we did all of those, and I will, I've got the paper here. So can you see the paper or not?
So if you don't mind, I mean, can we just like leave it for like an offline discussion after?
That's fine by me. Thank you for the question. Thank you all.
Yeah, would be interested.
For your time.
I like this interface with dynamics. So I would be interested in a longer discussion with you as well. Yeah.
Thank you all very much. I'll stay around as long as I can. Thank you all very much.
Thanks a lot. Thank you very much. Thank you.